Hey, Kevin, let's get started. Hi everyone. My name is Yuan, and welcome to the 2024 and the 2025 season January User Code Contest Silver Level Live Solution session. And today our lecturer is Arwen. He's one of the lecturer at XCamp for several years, and he has been helping lots of students uh, construct the solid knowledge foundation and enter the Grandmaster program at XCamp. And he also taught many of the students who eventually entered the US national finalists. And at the very beginning, I will start with a quick video introduction to XCamp, given some of you may probably know XCamp or enter the section for the first time. Oh, I saw someone said they cannot hear the sound. I will just replay it very quickly. I think it's because I'm using an AirPod. Sorry about that. Okay, I'll get started again.
Computer science and artificial intelligence are tools that will change the future. XCamp Academy is a community dedicated to inspiring and cultivating the next generation of computer science and artificial intelligence talent. XCamp Academy was founded in August 2017 in Silicon Valley by two Google software engineers. The name XCamp was inspired by the variable X, which represents unlimited opportunities. XCamp's curriculum system and training methodology is inherited from Mr. Xianyou Xu, a Chinese diamond level international gold medal coach. Our staff here in the US is mostly composed of senior software engineers from tech companies in Silicon Valley and prestigious CS students from top universities. In addition, we have strong support from international and domestic competition winners in our coach team. From beginner level Python to classic C++ courses and competition honors courses, XCamp's curriculum is designed for students of all different levels. By participating in team-based competitions and facilitating frequent group study sessions, XCamp also fosters an environment of collaboration to build each student's confidence in their ability to code. As of mid-2024, more than 300 XCamp students have reached the USACO Silver Division and above, including 60 in the Platinum Division, and 27 were selected in the US and Canada national camps, out of which 15 were fresh in the 2024 season and 2 were selected for the US national team. In renowned high school contests, Stanford's ProCode and UC Berkeley's Calico, and other prestigious US programming competitions, such as the Harvard Programming Invitational, Teams Code, and Lexington Informatics Tournament, XCamp students perform well, and we encourage students from being participants to problem writers and organizers. Our students received 13 MIT offers and many more from Stanford and UC Berkeley, thrilling us all. Here at XCamp, we believe that children have unlimited potential and can change the world through coding.
Okay, so thanks for watching the video. Over the past several years, XCamp has been dominating the user code in the US, especially as an institute located at Silicon Valley, and we've had more than 300 students got user code silver level and above, and more than 60 got user code platinum, and 27 students entered the user code camp as a finalist, all Canada camp. And we have one EGOI gold medal, one EGOI silver medal. And the one student, Brian Shear, he got the third place in the IOI in Egypt last year, and he got the gold medal. We are very glad to support more and more students in your journey to USACO. and we hope to help you. And by helping you, we really mean hosting different effort to support you. The first one is the on-site camp. The summer camp this year is going to be from July 21st to August 1st. And it's going to be in the Bay Area. We have winter camp too. And these whole day camp are very, very good opportunity to provide you with immersive experience to really spend those several days in coding, in problem solving. The point is not to teach you too much about knowledge. The whole point is to get you enough muscle memory, practice more, and also understand you have lots of friends, lots of students, peer students that are studying the same subject like you do, and you are not alone. The second thing is the year-round weekend classes. We use these classes to teach you knowledge and help you to build knowledge base week by week. We try to break down all the knowledge into bite size and help you to construct your knowledge over time. And then the third thing is USACO mock test class. It's essentially a simulation of the real USACO mock tests. Sorry, real USACO tests. And also, you can also choose to use the past USACO real problems too. But keep in mind, the past problems could be easier, especially the early years. And also we have the Grandmaster class, which is taught by some of the most competitive competitors in the world in USACO and also in competitive programming in general. And Alvin is one of them. And we have if you want to shoot for USACO Gold, Planetarium level, and also finalists or IOI, then this is a class to go. Last year we have 15 students in the Grandmaster class got into the US camp and also Canada camp. And we have more than 10 students got the MIT offer from this series class as well. Lastly, we have the APCS preparation class as well. Okay, I will turn to Arwen to give you lecture. Arwen, you want to share a screen, right?
Yeah.
Okay.
Hey everyone. Yeah, so I'll go over the USACO silver problems. Yeah. So I'll just first tell you all my thoughts on this. Yeah. Yeah, interested to hear what you all thought too. Yeah. So yeah. When I looked at this, I felt problem 1 was the hardest, and then 2 and 3 were easier. So maybe to pass, one way to do it is to get full on 2 and 3, and then get partials on the first one. But yeah, let's get into the problem solutions. Yeah, so the first problem, yeah, we can go over the first problem first. Get this pen. Yeah. So yeah. Yeah. So you have like cows in a line that are species AI. And then yeah. And then you'll perform a checkup on a cow if its species is BI, right? And then we want to consider the number of cows that have a checkup, right? So in this particular case, there's 0 cows with a checkup, but you can also do an operation exactly once. Oh, like, yeah, you have to do an operation exactly once, right? So you take any, yeah, so you take any contiguous subarray and then you reverse its order, right? So the answer for this case is 3, because you can, yeah, yeah, yeah. So if you flip this subarray, then you'll get 3, 1, 2, and then this 3 will match with this 3. And I think there's 6 subarrays in total that you can match, and these 4 will cause some cows to be checked, right? Yeah. So then the answer will be 3. Yeah, I think there's also another sample input here, right? And then yeah, so these are constraints. Yeah. So one way we can think of this problem is yeah, Cynthia, you have a question?
I already know exactly how the brute force strategy works.
Okay, cool. The
Although
N
what I want
5,000,
to hear are the optimizations.
right. So we'll go over brute force first, and then we'll talk about how to optimize this. Right. So for N up to 5,000, so basically like whenever something counted, it's because there's a match of some AI with some BI, right? It's because this is A and this is B. And then there's this index I and there's this index J, right? Yeah, and then this has some value X and yeah, and then this has some value X, right? So when you flip this, then they go into the same position. So idea for n squared is count contribution of each AI BJ pair, right? And in order for this to match with this, basically you're gonna flip this box, and then basically you flip anything that has this box in the center, right? So you can flip this thing in black. You can also flip this thing in pink. You can also flip this thing around it, right? So the contribution of each AI BJ pair is going to be min. So it's going to be min of there's right, there's I options for the left endpoint, right? It has to contain this. And then the right endpoint has to have the same length as the left, right? And then there's n minus j plus 1 options for the right endpoint, right? So the contribution of each AI BJ pair is going to be min of I plus 1 and n minus j plus 1, right? Yeah, so you can consider the contribution of each AI BJ pair where they're equal to the same value X, and then you can add this value to the answer, right? So that gives you the solution. Yeah, so you can just loop over I, loop over J. That'll be a nested loop, so that'll be n squared, right? And then for subtasks 6 to 9, all the things are generated uniformly at random in the range 1 to n, right? So what that tells us is that each value x, x occurs roughly 1 over n fraction of the time on each array. So it's like roughly O of n occurrences in each array, each of A and B. So the same solution will also work for the subtask where it's randomly generated for things from 1 to n, but you shouldn't write a nested for loop here. What you should do instead is you should store, one way to do it is you can store like the occurrences of x in each array. So yeah, so maybe like awk A is like a list of the indices where x occurs in A. And then you can also have awk bx, right? And then how you can do this efficiently faster than n squared in this case is you can do for I and awk A, for J and awk B. So then you add this quantity star to the answer. Right. So the n squared approach, it's going to work for test case 4, test case 5, and then test case 6 to 9, right? So we want to be able to do this more efficiently, right? Yeah. So let's consider the same kind of approach where you want to find the contribution of I and J pair with the same value. But let's just say in the array A, you have these occurrences of X over here. maybe X.
Wait, it's pairs?
Um,
Pairs?
so the idea is,
Like,
right,
so what exactly do you count as a pair? Like two things where they match?
yeah,
And how do you calculate the contribution?
yeah, I can explain that. So like if you have A and B, the problem is you're flipping some array, right? Subarray, you're flipping this subarray. And if there's X over here and X over here, then flipping this subarray will cause these two things to match, right? So I'm counting the contribution of each ij pair, basically each ij pair, one where it's an A, like AI and BJ were equal value, they contribute to the answer for some LR reversals, right? And the subarrays for which these pairs contribute are the subarrays that contain this as the center.
Wait, I have
Yeah.
no idea. So how do you calculate contribution?
Yeah. So like if you reverse this subarray from I to J, then these two things will match. X will go over here, right? So then they'll match, right? And then all the subarrays for which they'll match are ones that include this as the center. So it's going to be like subarrays of the form from I minus K to J plus K, right? For any integer K, if you reverse this, then they're going to match, right? So yeah, the formula we showed earlier was min I minus 1, sorry, min I and minus J plus 1. Yeah. I can go into this a bit more at the end, after we
You mean
finish going over.
specifically, so it's basically like number of subsequence is sharing the same midpoint or center.
Yeah, number of subarrays sharing this midpoint. Yeah, exactly. Yeah. So let's consider the full solution. So let's say there's occurrences of X. So this is your array A, and this is your array B. Oh gosh. Okay. Yeah. Yeah, this is your array B. So brute force was just considered one of these as I and one of these as J. But we can do this faster. So basically there's two cases, right? Either I for I and J, this X is from A, and then this X is from B. So this is case one. So if there's an X at index I in A, and there's an X at index J of B, then we can reverse them, and we can reverse anything that contains this. And then this ends up being like, there's two symmetric cases. The first case is AI is equal, like the left one is from A, the right one's from B. The second one is where the left one is from B, and then right one is from A, right? Yeah. So these are the same kinds of cases. So let's just focus on this case, right? So what we can see here is, let's say that let's fix I over here, right? And then let's consider different values of J, right? So J can be over here, J can be over here, J can be over here, right? So up to some point, so we know there's like I subarrays that contain like the range from I to J, but after some point, this thing here, if this is equal to J, this is going to be like less than I, right? So for some like prefix of these J's, you're gonna add like I, right? You're gonna add plus I to the answer, for some prefix, I'll just write more. You're gonna add plus I to the prefix to the answer for some prefix. And then after this prefix, you're gonna add plus something. I think you're gonna add plus n minus j plus 1 plus n minus j plus 1, right? So up till some point, you're gonna keep adding plus I to the answer, and then after some point, you're gonna add n minus j plus 1 to the answer, right? So this is for a single I, if you fix this I, and if you go to the next I, then yeah, then I is going to grow bigger. Then maybe this one is also going to turn into n minus j plus 1, right? So the idea we can do here is we can maintain 2 pointers, and I'll
Wait,
just draw. Yeah.
I wonder, what's the optimization?
Yeah. So I'm considering it solving for each distinct value separately. So yeah, I haven't actually talked about the algorithm yet, but this is just like the sum you need to make. It's going to be plus I for some prefix, and then plus n plus j minus 1 for some suffix. So basically, when I is over here, up to some window where this is R, there's going to be a bunch of plus I's, plus I, plus I, plus I. And then after this R, you're going to keep, these are occurrences of X. This is occurrence of X. And then after this R, you're going to add n minus j plus 1 a bunch of times. N minus j plus 1. And the idea is, as you increase I, R is also going to decrease. So some of these things are no longer going to be plus I. They're going to change to n minus j plus 1, right? So this will be a 2 pointers approach. So the time complexity will be O of number of occurrences of X.
I don't understand.
So basically what I'm doing is for each I, I'm solving for all the j at the same time, right? So we're considering the first case where I is to the left of j. This is my array A, and this is my array B, right? So initially in the brute force solution, if I is over here and j is over here, then we have like I times n minus j, or min of I and n minus j plus 1. But if you consider all the things at the same time, if you fix I, then for a prefix of these, you're going to add plus I to the answer, because you can extend the subarray that contains this only up to I, because after that, it'll overflow here, right? And then after that point, if there's another element at some index j, then you might not be able to extend it I times because it'll overflow. So you can only have n minus j plus 1 subarrays that contain it. Yeah.
But then what about the part where you still have to make a sum of the number of contributions?
Yeah, so that's what I'm doing here. So I'm basically what I'm finding here is contribution. So fix I. This is my fixed I, and then I'm summing contributions over all of the j's. Sum contributions over j greater than I and B. And the sum of the contributions, it's going to be of the form plus I for some prefix. And then after the prefix will be n minus j plus 1, n minus j plus 1. Yeah, we can also go over this at the end, just so I can have time to go over the other 2 problems. Yeah, but yeah, the high level idea.
You mean
Yeah.
For some extra clarity, so when you start, you place I at index 0, then you place j at index 1. There's like . for that pair,
Yeah, sorry. We can go over this at the end, but yeah. How I did this is I stored the indices. Those actually ended up being very tricky to implement. Yeah, this is probably the hardest part of the contest when I did it. Yeah. But this is the solution for problem one.
wait, so like you pick a center point and you count how many subarrays share that point.
That's what we did for the brute force. And yeah, you could do the same thing here, but you do it for all pairs. So you fix I and you do it for all the j at the same time. So for this pair, so for this pair, there's a center here. Like if this is j, this is the center. If this is j, this is the center. And it's possible to show that it's in this form, plus I, plus I, plus I. And after that will be n minus j plus 1, n minus j plus 1, where j is the location. Yeah, don't worry too much if you not fully understand the details. We can also talk about this at the end. Cool. I'll move on to problem 2. Yeah. Yeah, so the problem is so you have an array of integers. And then and then basically on your array you can perform an operation. You can add one or you can subtract one, and you want all of them to be divisible by some number m, right? And the question is asking over all possible x to add to all the elements of the array. You want to find the minimum number of operations you need to make them all divisible by m, right? Yeah. So in this so in this example, so if you subtract using x equals 3, then you get this array 12, 9, 15, 0, and 5. And I guess m is equal to 9. And then the answer is 10 because you subtract by 3, and then plus 0, plus 3, and then plus 0, and then plus 4, and then 3 plus 3 plus 4 is 10. So the answer is 10. Right. Yeah. Yeah, and there are a few brute force subtasks which you can just do using brute force. But let's talk
I only
about
passed the first case.
what?
I only passed the first case.
Oh, like the sample?
Yes.
I see. Yeah, so let's talk about how you can do this problem. Yeah, so notice that, like, let's say like a1 is equal to 0, and let's consider what happens when you add a number, or to the cost as you add a number x to it, right? So let's just pretend this is plus, so it doesn't matter, because it can be a negative integer too, right? So when you add an x, so x, and then we can graph x over the cost, it's going to be of this form, kind of. It's going to go up and down and up and down, right? I'm simplifying it a little bit. I think there's some small details, extra details when m is odd, but this is effectively what's going to happen to the cost to fix it, right? It's going to go up and down, right? And then if you have like a2 is equal to 1, then the cost to fix it will be something like this, right? So the cost to fix a2 will be something like this when you add x, right? So the total cost, it's going to look something like this, right? You're adding 2 lines, it's going to look something like this. This is not the greatest drawing, but it's going to look something like this, right? So the goal is to minimize the sum of the costs, sum of costs over X, right? So you have a lot of these kinds of hills and valleys. And the cost is going to be the sum of all of them, right? And one thing to notice is that like the slope is equal to 1 here, and slope is equal to -1. And then slope equals 1, and slope equals -1. So when you add this, like these slopes also add, right? So slope is equal to 2, slope is equal to 0, and slope is equal to -2 here, for example, right? So when you add these things, the slopes add, right? So this is a problem that you can solve using a line sweep, right? So at t is equal to 0, you can compute, at t is equal to 0, you can compute like, you can use brute force to compute cost to fix everything. Sorry, not t equal to 0. X is equal to 0, you can compute the cost to fix everything. And then for each AI, you get this kind of hill valley thing, right? So what you can do is you can do a sweep from the left to the right. And then for anything like this, you're adding like +2 to the slope. And then for anything like this, you're adding -2 to the slope. And then here you add +2, and so on, right? So how you can implement this is you can set like your current X to 0. And then you can set like the current slope. You can compute this beforehand. And then as you go from left to right, you also need to know how the slope changes, right? So for this specific index I, you know this at this point the slope will change by 2. At this point it will change by -2. At this point it will change by 2, right? So you can have a map. You can store in a map the changes of the slope, right? Map into int deltas. So deltas I, it'll be what the slope will change by when we set x equal to I. So change in slope when x is equal to I, right? And the key thing here is, yeah, so we only need to consider this up to m, like from 0 to m, like x from 0 to m, right? Because it cycles after every m things. So x equals m plus 2 is going to be the same thing as x equals 2, right? So we only need to consider x from 0 to m, right? And then we can do a sweep over the deltas. So we can do something, for example, like for x in deltas, and then you also need to maintain the current value. So you need to compute the value in the beginning, and the slope in the beginning. So yeah, so like just the math will look something like cur val plus equals cur slope times x minus cur x, and then cur, oh yeah, so this is a map. So yeah, and then deltas, so cur slope plus equals y, yeah, and then answer is going to be the min of answer and cur val, right? So the key thing is, since the x from 0 to m are the only relevant ones, then the only points in this thing that matter, only like a constant number of points matter for each element, right? So this deltas map will have O of n amount of info. So
What?
the time complexity here, so the time complexity will be n log n, right? Any questions?
Wait a minute. I don't know how this works.
Anything specifically that you're wondering about?
Specifically, are you going to take the mod of every number?
Sorry, for what exactly?
Aren't you going to take the mod of every number?
For what reason? Or like which
So
numbers?
like, basically go through each number and mod it by m.
Like in the input, like mod this by m.
Yes.
Yeah, so that's a good way to simplify it. That shouldn't change anything, right? Yeah, so you can.
I mean, to be honest, in my algorithm, it was critical
Okay,
because it doesn't work.
I see.
Continue.
Yeah. The idea I'm using here is that as you add some value x, the cost changes in this kind of zigzag pattern, right? So as you add more, then it's going to cost more. And then after some point, it's going to go down. So for example, like if m is equal to 2, the cost from 0 to 0 is, so the value, let's just consider the values and the costs. To round 0 to a multiple of m, that's 0. To round 1 to a multiple of m, that goes down to 0, so that's 1. To round 2 to a multiple of m, sorry, I meant to write m equals 4. Sorry. To round 2 to a multiple of m, you can either subtract 2 to get to 0, or you can add 2 to get to 4. So the cost will be 2. And then to round 3 to a multiple of m, you add 1, right? So that's cost of 1. And then to round 4 to a multiple of m, it's already a multiple of 4, so it's 0. And this keeps cycling, like 1, 2, 1, 0. Which is why I said it has this kind of structure, zigzag structure, right? It goes up and down and up and down, right? So as x increases, this is how the cost changes for a single AI. And then for another AI, the cost might change like this. Yeah. And then, as I said earlier, the goal is to minimize the sum of the costs. So you can find the relevant x values, and you can do a sweep from left to right, and maintain the values and the slopes.
Wait,
Yeah.
how do you calculate the current slope?
Yeah. So the info, yeah. So like the slope at x equals 0, you mean?
Yes.
Yeah. Yeah, so there are some details in the implementation, but we can look at a couple of cases. Like if x is divisible by m, so if if m divides, or x is 0 mod m, sorry, not x, right? AI, so this is for the case x equals 0, 0 mod m, then the slope is 1, right? Slope is 1 here. And then there's other cases, might be -1. Yeah. Yeah. So these are the cases. Yeah. I think x odd is different. There's like more details, but in general, how you should think about it is, yeah. You compute the slope for each element individually. It's going to be 1 or -1, and you're going to add all of them. And that's how you find the initial slope. And also that's also how you find the initial cost, right? And then you have this map of deltas, right? So we have that, we know it has some zigzag pattern. So the slope is going to change by -2 over here, and it's going to change by +2 over here. So if this is x, then you can do like deltas x minus equals 2, right? And once you've computed all these deltas, then it becomes a sweep, right? So you have for x, y, and deltas, where x is the x value, y is the change in the delta, then you change the current value based on the slope, current slope, and then you change the current slope by y.
Is there anything simpler than this?
Not that I'm aware of, but it's possible there is. Yeah, but I think this is yeah, I guess this is a form of line sweep that comes up from time to time.
Line sweep. What happens when n is greater than 2?
N is greater than 2, right?
Yes.
Yeah,
In the
so
in your example, n is equal to 2.
yeah, so I just wrote two of these just to give us some intuition, but yeah, you can have more of these, right? Oops. Right, so you can have this zigzag here. Sorry. Yeah, so let's say we have this zigzag here. It'll be the same thing we do, right? So at this peak, we're gonna add -2 to the slope. And then at this valley, we're gonna add +2 to the slope. Then at this peak, we're gonna add -2 to the slope. Yeah, but since we only care about x from 0 to m, then for each set of hills and valleys, we're only gonna only like 3 or 4 of these things will be relevant. So the size of deltas, the map we have, is gonna be at most like 4n. Yeah.
I don't understand. Like, well, does that say, what does all of this even mean?
Anything specific you're asking, or sorry?
Specifically down here, is that curve slope x? Why is there an x there? X
I'm
before
not
the
sure what you're pointing.
parentheses.
Oh, curve slope times. Yeah, this was a time symbol, right? Yeah, because if this is correct, and then this is x, then the value at here, so this is curval. So it's going to be
What is
to compute the value, if you know the slope, then it's going to be the slope times x minus curx. Yeah.
But what's different? How is regular x different from cur x?
It's just the way I named the variables. I guess like there are many ways to do this, but x and y is just they're the events I'm iterating over. So they're the times when the slope changes. I think I missed a line, so yeah, at the end I have to write for x is
What
equal
does
to
deltas actually store data for?
what?
What's in deltas?
Yeah, so deltas I means that the slope is going to change by some value when x is equal to I. So in the example where it's just one zigzag, deltas will be -2 here because the slope changes from 1 to -1. And then over here, deltas is going to be +2 because the slope changes from -1 to 1. And then deltas is going to be -2 because the slope changes from +1 to -1. Yeah. And then for the case where you have multiple zigzags, you have to add all the deltas to get the change in slopes. Yeah. This problem was a little bit tricky to implement, but yeah, is the idea. Yeah, and you can feel free to make a post on Discourse or ask if you have any other questions later. Yeah, so let's go over problem 3.
Wait, slope change when I equals when
X is equal to I. Yeah.
wait, which x do you mean?
the x that you're gonna add to all of your elements in the array.
Wait, well then, if delta stores the slope change when I is equal to x, it would not actually store the location of where.
So I is the location, and then the key is, so it's a map, right? So the key is the location, and then the value is the change in the slope.
Value is change of the slope.
Yeah.
And what's the index?
The index is the location. Right? I can also call this delta as, I'll still say delta is I. Yeah. Index is like the location of x, right? So at this location, the slope is going to change by some amount. Yeah, I think we're almost out of time, or we have just enough time to go over the third problem. Yeah, but you can feel free to ask any questions later. Yeah. So let's go over the third problem. Yeah. So I personally found this to be more straightforward compared to 1 and 2. So let's
I
go over
mean,
the,
I
Yeah.
kind of did a long-winded implementation where you count the number of occurrences and create a key for converting back.
yeah.
Then you look through the original array and see which one comes first in order to rearrange the key in such a way that it becomes lexicographically smaller.
Yeah.
However, there's one problem with that. It has no way to make sure, it has no way to take into account the fact that the biggest and smallest of each row must have a constant difference.
So let's go over this problem, right? So I guess you observed that like it has this kind of thing, right? So 2 occurs once, 3 occurs twice, 4 occurs. I'll just go over the problem really quickly.
That's basically a principle I used.
Yeah.
But does not take into account the property that the largest number and smallest number difference is always constant.
Yeah. I guess I should go over the problem briefly for everyone. Yeah. So there's some kind of addition table, right? So Aij is equal to I plus j, and it's going to look like this. And there's 3 types of operations. One is to swap 2 rows, one is to swap 2 columns, and the other one is to swap the occurrences of A and the occurrences of B, right? And it's guaranteed, yeah, 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 so it's guaranteed the answer exists. So your input is going to be, yeah, it's going to be the table after all the permutations. Yeah, and I guess an observation here is that 2 occurs once, 3 occurs twice, 4 occurs thrice, 5 occurs twice, 6 occurs once. And given that we know where 2 is, 3 and 4 have to be on the same row. And then 3 has to occur twice, and 4 has to occur thrice. And then given the occurrence of 6, then we can find where 5 and 4 are, right? So the key observation is that there's only 2 cases for what this table should look like before operation 3, right? So we can take a look at this case, right? In this case, this thing occurs once and this thing occurs once, right? And then we have that one of these has to be 2 and one of these has to be 6, right? And we can just consider the 2 cases, right? So if this is equal to 2 and this is equal to 6, then we know that both of the neighbors of 2 have to be 3 and 4. And since 3 occurs thrice and 2 occurs twice, then there's going to be 3 and there's going to be 4. And similarly, we can conclude that yeah, since 5 occurs twice, then it's going to map to 5, right? So yeah, so the idea is that like the location of the elements that occurs exactly once gives us, if we assign these, then that gives us enough information to construct the whole table, right? So there's only two possibilities for what the answer should be, right? So it's the solution is just try both cases, and then see which one is lexicographically smaller, right? Yeah, I went through that a bit fast, but any questions?
Well, I'll show you what kind of happened I was about to show you what's happening in the larger sample, except I cannot access the contest page.
One sec.
I'll show you what is going on. What it does is
Derek asks, where can I find the problems? I don't think they're available, but you can screenshot. I don't know if it's the best way to do that.
what happens is that in my sample output, the difference between the highest and low of each row is not constant. For example, in one of them, the largest number is a 10 and the other is a 6. But in the other, the largest is an 8 and the smallest is also a 6.
Yeah, so I suggest to ask a question in Discourse.
So in that case, that it would probably be just brute forcing everything.
Yeah. Wait, Brian, I just saw your message. So go over the last partial for problem 1.
Using really messy code.
I can quickly go over the last problem for partial 1 before they start the gold. Yeah. Yeah, we can, sorry. So I think when I did this problem 1, like I initially solved it for 4 and 5, and then I saw my solution works for 6, 7, 8, 9. And then I did the last case separately. Yeah, so my idea for the last subtask, so I guess there's 2 cases, right? So if this is A and this is B, so we want to find the contribution of like AI BJ pairs, right? So there's 2 cases, right? Case 1, there's also like the edge case where they're equal, but I is less than J. And then case 2, IJ. Case 2 was I is greater than J. And then you need to reverse something with the center here, right? And these 2 cases can be dealt with the same way. So let's just consider this case. And what I did was you solve for each x separately. So you have x's in A and you have x's in B. And you just need to know where the indices are. And then we can fix I here. And then consider what happens for all j's, right? So we can say there's also x here. So for some prefix, we can extend this by I, and then we can also extend this by I. So for some prefix, the answer is going to go up by I, and then for some suffix, the answer is going to increase by n minus j plus 1. Right? And then the idea is you can do it 2 pointers by increasing I. And then as you increase I, you can keep like some threshold where it changes from plus I to plus n minus j plus 1, right? And as you increase I, this R is going to decrease. And basically for this window up to R, it's all going to be plus I's, and then it's going to be n minus j plus 1. So you can use 2 pointers to maintain this. Yeah.
This doesn't even look anything like the original problem.
So it was like in the original problem, I was considering an I here and J here, and then finding the contribution of this to the answer. And I'm solving the J's as a batch for each I. Brian said only the subtask where 1 and 2 are the only values. Oh, I didn't try solving that, so I'm not sure, but maybe there should be a simpler way to do this. I don't know.
Okay, thanks.
Thank you. Yeah. Cool. So that's it for the silver problems. Yeah. Thank you. You can
Optimization doesn't even sound like anything remotely related.
feel free to like send an email or ask on Discourse if you're confused.
Which discourse?
XCamp Discourse.
XCamp, which category?
I mean, there should be some category. I'm not too familiar. I'm sorry. Yeah, but I'll stop here. Alright. Yeah, you can ask in general.
In general?
See you and message.
Wait a minute. So what I mean is that although at least your original n² solution was a huge improvement anyways.
Yeah, I guess I'll just suggest like try to think about it and then yeah, right. Like if there's something you're confused about, you can ask in Discourse. Yeah. Great. Yeah, so I'll stop here. Thank you, everyone.
Yeah, thanks, Ivan, for hosting the silver solution section. And we will wait for 2 more minutes to start the gold section. Yeah, and if you have more follow-up questions, feel free to post in XCamp Discourse. And I think in a few days.
Should I leave now?
Yeah, you